Thank you. So then we come now to the point that we just introduced before the break. That is the method of lines. And that is not only valid for parabolic PDEs but also for hyperbolic PDEs. So what it means, we discretize in space like we did for studying the different methods, and get what we call the semi-discrete problem. And that means we have the space discrete, so that we have already done the discretization of that, and that we have the time still continuous. And that is what we get is then a system of ODEs. So with that we get a system of ODEs. And in the case of the finite difference method, then they are defined just at the nodes, at all the grid points. That we can take then as an example for what is happening. So we get an x, we have our interval xa to xb, and if we write out here the u, then we will have, if we do it in a similar way as there, we'll have the boundaries, and at the boundaries we will have, say, the boundary conditions, say the UA we call it, and then in the interior we have just a very few grid points here. We would have that would be our x1, and we would have the u1 here, and we would visualize it by these lines. We have it would be the 0 for the u, it would be here. We would then have the x2, we would have the corresponding u2, and let's see, we would have, say, here the u3, and that would be the ub, it would be again a boundary condition, ub. So then we visualize then what is happening at the grid points, so that would be the x3. So therefore this technique has gotten the name method of lines. So this approach is called method of lines. So we want to study that for solving the heat equation. The example is heat equation. The method of lines for heat equation. So what we do is we first approximate, would be our equation 4, the second derivative. Now we have a partial that is with respect to x, xj, we have the time dependence. So that is then approximated by the second difference operator, which is ux squared uj, divided by delta x squared. And as you saw yesterday, that is uj plus 1 minus 2uj plus uj minus 1 divided by delta x squared. So now we can insert that into our heat equation 1. Insert it into 1, we obtain the following. So we have the time derivative of u, and that is at the grid point j, that is the uj, duj dt. So that is what we get at the grid point j. Of course, we leave the time still continuous. And that is then equal to alpha. And there we use now the approximation. So here the time derivative is not approximated, but the space derivative is approximated. Then we use this approximation here. So then we use uj plus 1 minus 2uj plus uj minus 1 divided by delta x squared. And that we use at all interior grid points, which in the notation was from 1 to nj minus 1. And I remind you to use the j max notation, it would then be from 2 to j max minus 1. So that is usually the one that you would do in MATLAB, because MATLAB doesn't have the index 0. And we use then the boundary conditions. And the ones we are using, I mentioned it, I think it, but didn't write it. They are the Dirichlet boundary conditions when we give the values itself. So we then have the u0. Now I use again this notation here. Is then the ua, that is the boundary condition at the left boundary. And at the right boundary we have then, and that would correspond to the grid point nj, we would have the ub. And correspondingly, if we would do that with the j max notation, that would be then our u1, that would be the j max. So this equation that we have here, that is now our semi-discrete equation that is then obtained by only doing space discretization, leaving time discretization still continuous. So there we do not do any approximation. So then, equation 5 is the semi-discrete equation of heat equation 1. So you see clearly what it means. Space is discrete, and it's no longer the second derivative of u, but it's now only presented at discrete points. But time for each approximation at each grid point is still continuous. So that is then what we do by the method of lines. And what we can also note when we look at it more carefully, what we have here is actually a system of ordinary differential equations. So 5 semi-discrete equation that we derived that constitutes a system of ODEs. And then we are back to business, because then we can use the methods that we learned when we discussed the time discretization to discretize this system. We can express that in the following way. We can say this is corresponding to, if we write now u here now, it's representing a vector. So if we would do that in a book, it would be a capital or a bold faced u, and the right hand side would have a bold interfaced R. It's a function. Formally we would write it as we would do in MATLAB, always as a function of t and u. And this u, both u and the both r, they are the following vectors. So where with u, so u is equal to our unknowns. What are our unknowns? You see it here. Our unknowns are the values at the grid points. They are from that notation from 1 to nj minus 1. So it means they are u1, u2, and so on. The last one is u nj minus 1. So that is the vector of our unknowns. The values at the grid points. And they are all time dependent. Like you see here, this is just where we stopped at the time instant. We saw the dynamics before. And this bold R, that is then the right-hand side. And then we have to translate this right-hand side just into a vector. So we start from j equal to 1. First we know that the alpha divided by delta x squared we can write in front. That is the same for all. And then we get a vector. And then we have to do that for j equal to 1. So we get here u2 minus 2u1 plus u0. And for the u0, we use the boundary condition. So then we get here u2 minus 2u1, and here we use the boundary condition. The next one for u2 is u2, that will be u3 minus 2u1, 2u2 plus u1. 3 minus 2u2 plus u1. And that will continue all the way until the next but last. It will be at nj minus 2. Then we'll get here nj minus 1 minus 2u nj minus 1. That is not correct. That must be nj minus 2, yeah, right? Plus u nj minus 3. So that will be at nj minus 2. That is not the last one. The next to last. The last one is unj. But there we take the boundary condition. We take ub. Then minus 2unj minus 1 plus unj minus 2. So that is the equation that we get when we take the last one, nj minus 1, and we use then for unj the boundary condition. So that will be our, so that will be the vector. We also have this in exercise 4, that we will then program as a function, the MATLAB function, so that ODE45 or any other MATLAB inbuilt ODE solver can use. So you see here we have an n minus 1 vector by that. And then we just put it into ODE45 and so on. And then you'll see how MATLAB deals with that compared how you will do it with using the methods that we'll see next. Okay, so in this way, PDEs are not the problem at all. You just get it into this form, an ODE problem, and then we solve this ODE problem. That's it. So, but we want to do that not only with the MATLAB, we also want it to do ourselves, to do our own code, and see how that our own codes can compete with MATLAB. Then we have control over everything, and we can see what is really happening. So then, as I said, we can use any method now for the discretization of this ODE system that we studied in chapter 4. So, examples of ODE methods to solve the system are the following. First example, again, as we know, again, that also as the first example for the discretization of ODEs, that is Euler's method. That will be our first choice. That will be also our first choice for exercise 4. How does that work then? Well, we just apply the recipe. We have the value of, in that case, of the vector u. I write it now in this way, it makes it easier, at the new time level. But now we have a little problem, because before we used the subscript to indicate the time level. But we have already used the subscript for indicating which node we are, the grid point. So therefore it is common in the notation to get now the time level as a superscript. We write it up here. So we write the un plus 1 in this way. It is then the value of our vector u at the new time level, n plus 1, is equal to the value at the old time level, un, plus, and now our spacing is now, we have also distinguished there, because we have now grid spacing in space, delta x, times that we call delta t. So that will be now delta t, and then times the right-hand side vector r. That will be taken at the old time level and to be the solution at the old time level. So that is the way how we shall write now things. And which this means for each component the following. Because this is a system. So the u's and the r's are vectors. Now if we look at each component, we get the following. So we get then at grid point j, we get at the new time level the value that we had at grid point j at the old time level, plus delta t times, now we should remember what is the r. The r is this and this. And we look now at the column j. So we summarize this vector here, and we write it in this form, together with the delta t, alpha delta t divided by delta x squared. So I have the delta t multiplied by this, so I put it here. So that is our vector appearing here. Now we have to look for the jth row, and that will be then uj n minus, that will be plus 1, minus 2 ujn plus uj minus 1, right? So that we will get for the jth component. And that is what Radar showed you on Tuesday already in the demo. So the values here of the neighbors and also the value here, they are at the old time level that we know. So then we can easily compute that. But we should be careful, because we should not overwrite the solution immediately, because this here depends also on neighbors, and so we should really carefully distinguish the new and the old time level. If we do that with vectors, the likeliness of doing errors is low. But if you do it component-wise in this way, yeah, there's a chance of doing errors. And moreover, in MATLAB, it is always advisable to use vectors and vector the capability of MATLAB, because vector operations, matrix vector operations, are much faster than if you would use loops for that. So try always to use these vector notation and the fast operations that MATLAB has on vector operations. It uses like the all into cache and uses the operation on the whole vectors at the same time. Does not need to take each time go to memory, get it into cache. That takes really a lot of time longer. So here the boundary conditions will then enter from in the first and in the last row. That are the boundary conditions. So then we can say also this, what we have here, that is then true from 1 to nj minus 1. As I already mentioned, the notation is such that here we see it, the ujn is the approximation at the grid point xj and the time level tn. I write that. So the notation that is quite common in CFD, also in the book. Ujn is the approximation of the exact solution at the grid point xj and the time level tn. So that is the grid point, and that is the time level. That is the grid point. So let's see, maybe that is the grid point index, so that is related to that grid point. Then we point to the j grid point index. So we can see that here, and that is the time level. Time level is then this one, the n, and it is then the n that appears also here. So then we see what these mean. And this method has also another name. It's also called forward time central space. So the method that we have here, it is 8, 9, this is the same thing. One vector notation, this is the component notation, is called forward time central space. Its acronym is FTCS. Scheme. Scheme is another word for method. If we think of it regarding accuracy, we have shown yesterday the second derivative approximation in this way is second order. So it's second order in space. And regarding the time discretization, if we are using Euler's method, we know it is first order. So it's first order in time, second order in space. We shall come back to that next week when we investigate this in more detail. So we shall see that the FTCS scheme 8, 9, if you like it, is first order accurate in time. That means, we write it as in order terms, it is O of delta t. And it is second order accurate in space. And that means that it's order delta x squared. So we have now dependence of the accuracy proceed both on space and time. And another thing that we shall see next week, that the method is stable, CTS scheme is stable, for, that would be 11 on the right here. The following is true. It's a certain parameter R is between 0 and 1/2. This parameter is, we already discussed that, is for the simplified structure. It is mu, in our case for the heat equation, it is alpha delta T divided by delta x squared. And sometimes I use also a name for that. I checked yesterday again in the literature. It is not so common, but I call it von Neumann number. This is stability parameter. And that has to be in this domain, and you shall see that is also something I really advocate to you, to violate that and see what the scheme does. What does the explicit Euler method do when you do not obey this rule? And you choose, for example, here not 0.5, but something larger. Okay, so then you can do the explicit Euler method to solve this discrete equation that we got by the method of lines in time. And then we have the FCTS, the forward time central space. So that is an explicit method, and it is easy to implement. Now we want to move on to look also at the implicit Euler method to solve this discrete equation that we got from the method of lines. So that will be then B. Equation 5 that we got from the method of lines is then solved by the implicit Euler method. So that means that we get, well, that our solution vector U at the new time level is equal to the one at the old time level plus time step delta t, and now this right hand side containing the space discretization is then taken at the new time level with the approximation at the new time level. So before we had n here and n here for the explicit Euler method, but now we have n plus 1. And that means for each component, the following. At the grid point J, the approximation there is uj at the new time level n plus 1 is equal to the 1 at that grid point at the old time level plus delta t, and now we gain multiplying also with the other terms that are here, which is then the alpha delta t divided by delta x squared. That was the alpha over delta x squared, that was a part of the R. And then the jth row is uj plus 1, but now at the new time level, minus 2 uj at the new time level, plus the approximation at grid point j minus 1 at the new time level. So then it will be this solved then at the component J. That we do for all grid points, and that is from 1 to nj equals 1. And the boundary conditions are then used for j equal 1 and j equal nj minus 1, as we saw before. And this method is sometimes, well, that is not so frequent as FCTS, that I think some people use, but the name for this method is also given in the book. It is according to the scientist who came up with that in 1949, Larsson. So the implicit method that we have here is 12, 13, we have combined component-wise, is sometimes called Larsson method. And we shall see also next week it is it's also only first order in time, because the implicit, like the explicit Euler method, they are both only first order accurate in time. So this order delta t. And it is, again, because in the same space discretization, it is second order as the explicit one, second order accurate in space. That means delta x squared. So that is similar to what we had before for the explicit Euler method, but it has now a very important difference compared to the explicit Euler method in time. This method that we are discussing here is unconditionally stable. That it is stable for all von Neumann numbers, or you could also say time steps that are rather equal to 0. R has to be greater equal to 0. So that was, to remind you, R was the alpha delta t divided by delta x squared. So to have a well-posed problem, you must have a positive thermal diffusivity. Alpha must be positive. Delta x squared, of course, is positive if we have delta x not 0. Otherwise, it would not make sense. And then it also makes sense to have delta t greater than 0. Otherwise, we wouldn't move in time. So this essentially means that R should be greater than 0, but there is no limit. You can choose it as we like. But that is only regarding stability. This doesn't guarantee at all accuracy. That is something we have to check, that you will also check yourself. So it is stable, you get results, but as you choose very large time steps, you cannot expect any accuracy anymore. Okay, so that is then the basics, but we'll do that in more detail next week. However, we should look into the discretization now once again, because this is more complicated now than the explicit Euler method. The reason is that these solutions on the right hand side, they are already at the new time level. So we get, in fact, here, we get a linear system. So that is something that we should look at now to see how we really solve it. So, and this component-wise equation that can be expressed in the following way. What we do when we have an implicit method, we bring everything that we don't know on the left-hand side, and everything that we know on the right-hand side. So then we get, moving that to the left-hand side, we get minus r, because we use now this abbreviation. So this is r. This is r. So we get that then on the left-hand side, the uj minus 1, n plus 1. And in the diagonal, we have the 1 already sitting there. We get here 2ur. Then take that on the left-hand side. uj n plus 1 minus r uj plus 1. n plus 1 is equal to the ujn. And that is true for all the grid points. And that that from 1 to nj minus 1. And that corresponds to a linear system. To following linear system. So we are now to translate that, as we've already done when we discussed the ODE for the finite difference method yesterday. We have to translate that now into a matrix vector form. So, what do we get? That is then the system called 16. We start with j equal to 1. J equal to 1, we get here u0. That will be taken from the boundary condition. We will move that to the right-hand side. So that will come later. So we will start here with a u1, so that we get as the first entry in the matrix will be 1 plus 2r. That will be our first component. So that will be then multiplying the u1. Write already the u2, and that will get, the u2 will get the minus r, so that will get from there, the minus r. On the right hand, and then we just have a bunch of zeros. On the right hand side, we'll have the u1 at the old time level. By the way, this is at the new time level, of course. And we have said we want to move this over. Gets with plus r times u0 is ua. The boundary condition. J equal 2. J equal 2, we have now here then u1, so then we get a minus r sitting here. u2, we get in the diagonal a 1 plus 2r. And here, multiplying u3 will be minus r. And this pattern will continue all the way down, minus r in the upper and lower subdiagonals and 1 plus 2r in the diagonal. So we get that down to nj minus 2. So let's see, that will be u nj minus 2. Then we will have a minus r in the off diagonal. 1 plus 2r in the diagonal and minus r in the lower subdiagonal. On the right hand side, that will be at the new time level. On the right hand side, we will simply have u nj minus 2 at the old time level. U nj minus 2 at the old time level. Here I forgot for the number 2 to write that this is then the U2 at the old time level. So this is the same pattern. And for the very last one, for nj minus 1, we will now get minus r1 plus 2r as we had before. So we'll have minus r1 plus 2r, that will sit in the diagonal, 1 plus 2r. And this r, we move over with plus r u and j, which is ub boundary condition. So then we have here the u and j minus 1 at the new time level, and here we'll have u and j minus 1 at the old time level plus r times ub. So that will be our system. Over here we have just zeros. So that will be our matrix A. That will be our unknown vector u, and that will be our right-hand side b. So again, we have to solve this system, and we have to do that in each time step. To get from one time step to the next, from one time level to the next, we have to solve this system. And we can do that in MATLAB, as I told you yesterday, with a backslash b. So we get in MATLAB we have a backslash b. And we'll see later how to do that with the tridiagonal matrix algorithm. Okay, and by the way, if we would have a time-dependent boundary condition, these guys would then have the value at the new time level. Right. That would be n plus 1 if we had time-dependent boundary. Here I assume they are not time-dependent, but if they would be at the new time level. Okay, so then you have all the material to do exercise 4. And so I suggest you to already to start with that, so you can have more profit from the lessons on Monday. We have again, as usual, 12 to 14 in K24 and from 18 to 20 here. And then Rada has the demo on Tuesday, and we continue then doing a little bit more analysis, what we skipped here, regarding accuracy, regarding stability next week. Okay?